Началось? Сейчас. До этого не должно было быть.
Не, он до этого шумы просто.
Это сейчас какой-то очень плохой звук.
Какой-то вот такой пронзительный звук.
А сейчас не стало лучше.
Не, в принципе, хороший, нормальный звук.
Звучит не очень.
Потому что нас слышно так же.
Раньше в настройках у БС было 2 микрофона, я мог отключить, поставить только один. Сейчас там только один микрофон. Чуть не прибыл замок.
Очень хороший, все слышно.
So we continue and finish discussion of the local properties modules. We proved the following statement last time. We proved that the module, zero module, all localizations, prime modules are zero. Okay. Also, this is the same thing as all localizations, all maximal ideals. So, in words, we can say that prime is zero, you can only give clockwise zero. Because we know that essentially look at this module at every localization, at every prime ideal. Sometimes those scopes of the module, it makes more sense when you discuss shapes, for example, algebraic geometry. This terminology is also used in algebra. Okay. From this we can immediately derive the following. It says the following, that m is zero, if and only if support a subset in the spec of R of all prime ideals such that corresponding localizations of the module are not equal to zero. So the support is in. There's also another version of the same statement, and the version is the following. I want to consider ideals generated by many elements, and these ideals are equal to the ring. So this is the structure that I want to consider. How can I think about this geometrically? Well, essentially, I can say the following. If this is true, then I can take step of the ring and say that the spec of the ring is the same thing as the union. That's when all these f's, i's doesn't vanish.
Phi is an element or is an ideal?
No, these are all elements. These are all elements that generate an ideal. This ideal has to be equal to the d. In this case, this is equivalent to saying that we consider open subsets where this thing doesn't vanish. This open subset will be exactly the cover of the spec of the ring. Well, that was the principal open subset associated with this element, and the definition of the following. If I want to understand what's the f of f, I just need to take this spec and just set that this element is vanishing. So these are all open subsets, they are called principal open subsets, and we know that they form a wave of the topology. But you can think about this also as an algebraic analog of the partition of unity. Remember partition of unity from the analysis is you have open cover on each of the open subsets of your function, which is supported on this open subset, and the sum of all such functions is equal to 1. So here you can think about these functions, maybe and 1 is equal to some sum. So in some sense this is analog of partition of unity, or you can think about this as covering of the spec by open subsets. So, and then thinking a little bit geometrically in terms of the spec, the following corollary is not very surprising. It says that if you choose such elements, if you choose such elements, then condition that localization every such fi is isomorphic, the module itself is zero. So we can check this condition that the module is zero if we do this forwards. We say the risk locally. So we have a cover, in this case this cover, and each of the subsets of this cover, the module is zero. Essentially you can see tensor product with the localization of the corresponding element, and this tensor product of this localization is exactly something that has support on the df that we saw in the seminar. So you can think about in some sense this localization as the restriction of the module to this open subset. So all the restrictions are zero, the module is zero. So in this terms it's a quite natural statement. The proof is not very hard, it follows from the proposition that we proved last time. So I can say that any maximal ideal of the ring, there is an index I such that, well, of course I is between 8 and 1, such an index such that I is in the R minus M. So in other words, I is not in the M. Because if all if I is high in the M, this cannot be the ring, this has to be proper ideal. That's not the case. Okay, so there is such a I, which is in the complement to the maximal ideal, and now I do the following standard trick at localization. I introduce new multiplicative subset, which in this case is just the image under the map iota sub R of the multiplicative subset R minus M. right? So you can do localization in two steps. You can first invert f, then the image of your, or you want to essentially localize with respect to this set. But you first localize with respect to some subset, in this case just a subset generated by one element, and then you can localize further using all other elements. So then you can say that the localization of the module M and the maximum ideal is isomorphic to the localization at T, and you localize relation.
There's T is equal to the IFI. It's IFI. So it's image under localization of FI.
So you first localize with respect to the element.
Yeah.
Right? Yes, thank you. And then you definitely image of a multiplicative set is again multiplicative. So you get some new multiplicative set, but now in the say localized ring. Then so you can localize again using this multiplicative set. But if you do this in two steps, you first localize the multiplicative subset and then the rest of the set, then you get just localization with the original set. Okay, but we know that this is 0, so this thing is 0. So for any maximal ideal, this localization is 0. By proposition, the module is 0. Proposition. This proposition is saying that you can check following criteria. So the first property is that the sequence. Here use the same logic that we saw when we discussed the localization of any sequence is exact. So I'm going to take any sequence essentially if I can show that this is exactly this term, I can preserve any all possible tests. So the second statement is of course as before that the sequence obtained by the localization of any prime ideal is exact. The condition number 3 that this has to be true for any prime ideal respect to ideal single spec. Focus again is relatively elementary, so we already know that 1 was true, and of course 2 implies 3 observations. We know that we localize anything with still an exact sequence, and then of course every prime ideal is maximal, so 2 implies 3. So the only trivial of course is to show that 3 also implies 1. So we know that all the localization maximal ideals are exact. We want to show that the original sequence is exact. Well, first observation, we take the image of the composition of the beta, the composition is alpha. Now, since this localization maximal ideal is 0, at least we can say that if I take this and localize the maximal ideal, I'll get 0. But now I just look at this image of the composition as a module. So this module localized at any maximal ideal is 0, so the module itself is 0. So this is for any M in this spec. By the previous results, we can say that the image, the composition beta and alpha is equal to 0. Or in other words, this immediately gives us that the image of alpha is contained in the kernel of beta. Now we can introduce the so-called homology module. So we don't really do any homological methods in this course, but well, if you don't know anything about homology, just think about this HSE definition. So this is the kernel of the localization, the kernel of beta modulo the image, right? So since we know that the image is contained in the kernel, this makes sense. And the only thing we need to show is actually that this module H is 0. But now, if I localize this at the maximal ideal, I can just as well put this localization here and here, just by the exactness. So this H is defined by a short exact sequence, right? So we have H, which is covered by the kernel, and the kernel of this cover is the image. So by exactness, localization at any maximal ideal is the same thing as the kernel of the beta M module of the image of the alpha M. But this we know that this is 0. So no homology for this short exact sequence. The kernel is the same. The kernel of the beta M is the same as the image of the alpha M. This is the exactness. Hence, this is 0. And again, since the localization of the module H is 0 for any maximal ideal, the module H itself is 0. This the original sequence in position 1 is exact. So we can check the exactness stopwise, and of course we can check the exactness locally. So again, if I take several elements, we get algebraic partition unity, and then I can say that the sequence, some modules, as before, M prime, M double prime is exact. All the localizations of all such FIs get exact. This is any I. I believe it was a little exercise, but it's not really required by this proposition, and the same idea. So some things we can check localized, something we can check the risk locally, but not everything. So for example, everything works in the risk local. Again, this is a set of elements generating the unit ideal, the MVR module, following proof that all such localizations M, Fi are finite, and for all i's we belong to M, so M itself is finite. So the property that we know doesn't hold for just localized or primary or maximum modules, which are one example and similar. So, and the second property, of course, quite closely related, assume that all such localizations are finitely presented. Sometimes people for shortness say FP. So I'm going to say FP for finitely presented. So all such localizations are finitely presented again for all n between 1 and n. So then the module finite itself is finitely presented. Let me fix the set of generators. So of course, I'm going to first prove first part and then the second part. So maybe this is the proof of the first part. So let me say that set xi inside module M so is the set such that if I take iota fi applied to the set xi that generates. We know that all such M of i's are finite modules, so they generate by finite sets. So there is a finite set of generators. In general, they would look like some mi over fi with mi, right? So this is a general form of any element in this module. But I claim that you can as well just take these denominators to be equal to 1. Well, since this is a module over localization in the fi, and all the such fi's are invertible elements. So if you multiply a generator by invertible element of the ring, you still get a generator. So without loss of generality, you can think this is mi over 1. And if this is true, the set of generators will be written in this form as localization, non-finite subset in the end. So remember that this iota is what is doing, you just take the element in the module and divide this by 1. So that's an explanation why I can say that there are such finite subsets xi inside M. Okay, now the next step is straightforward. You just take x to be the union, so that's a finite union all such xi's. So xi is a finite set, and this union is also a finite set. And then you have a short exact sequence as usual. You have r to the x. Now, okay, so clearly, well, first of all, you have a map like this. That's a bunch of elements. If you have any set of elements in the module, you can construct the corresponding free module and get a map like this. Now, I claim that this map is subjective. And the map is subjective because it's subjective if you localize any of these fi's. And now we use previous proposition, right? So exactness can, actually previous corollary of the proposition. Exactness can be checked at every such, it's such covered by these elements. And of course, I didn't mention it, but of course I need to say that if you can check exactness, in general, of course you can check subjectivity or objectivity by this property, and also bijectivity, because bijective is just subjective plus subjective. So you can say that if you have a map between two modules, it is subjective even only if localizations are subjective, and this is what I use here. So I have this map, and I claim this map is subjective by the corollary of the proposition. Okay, and now let's set K to be the kernel of this map. So we have the short exact sequence. Actually, even without kernel, I finished the proof of the first part, right? So I wanted to show that M is finite. Well, this is finite. This is finite set of generators. Now I'm going to need this kernel in the second part.
Sorry, what is Rx?
Well, this is just a free module generated by the set X. So just the same notation. For example, I can say that this is R to the quantity of X. Right? I just see how many elements I have in this set. This is a finite set. And just take as many copies of R as I have elements in the set X. So properly, I need to say that if I want to direct sum, but since this is finite set, direct sum and product is the same thing. So that's what just. Okay. So now let's go to the second part. So in the second part, I can see again the following. I look at the short exact sequence. I localize this exact sequence at some fi. So let me maybe try this. The sequence for any I. And now it is given to me that mfi are finitely presented. And this is a finite free module. So I know that this has to be a finite module. mfi finitely presented as mfi is finite. This is finite, and again, this is all finite. So localizations, such kernels, finite. And we already know result 1, so let's apply result 1 to these modules. All localizations are finite, hence the module is finite. This means that M is finite. So mfi and let's fix a multiplicative subset. If n finite and localization S inverse phi is surjective, set S such that localization of the phi at f is surjective. And the second part, if finitely presented finite requirements, that S inverse of phi is bijective, and again as before, this element f, the most is S, such that this element is bijective. At this point, some technical, maybe not very interesting solving, but we're going to derive several corollaries that are interesting. Yes. For the first part, so first of all, if I have any map of modules, I always have an exact sequence with 4 terms. I have m mapped by the map phi to the n, and then I have third kernel of this map. P is kernel of phi, z third kernel. We can say about this thing in the first case. So n is finite. Any motion of a finite module is again finite. C is finite. And what else we know? We know that localization of multiplicative set S of the map phi is surjective. So this means that when I localize, I get a map S inverse phi, which is surjective, so its co-kernel is trivial and localization is exact, so it can use with taking co-kernels. So S inverse of the C is equal to 0. So that's a finite module such that localization of this module is equal to 0. So now we're going to return to the very first proposition that proved the section about localization of modules. So remember that we proved one of the statements that was saying that there is an element, in this case, so there is f in the multiplicative set S, such that, there is f in the S, which is also in the annihilator of C. That was one of the statements that we proved. But if you localize C and this element f, the equilibrium is 0, because this is and we want this to be in the set S, so this condition is satisfied, S and S. And since this annihilates all elements of this zero, this is clearly 0 because to take any element, right, you can multiply this, divide this by S, and Fm is 0, since F is in the annihilator, so this is minus localization of the element F is 0.
But why is localization of C equal to 0?
Well, then I just explained this. You take
The localization of C by multiplicative set S.
Well, this is because we have this assumption that this localization is surjective. So you take the short exact sequence, you localize this at the S, then you get exactness, so we have this surjectivity here. So this means that the localization S inverse of C is 0. So this part follows from the our assumption. Okay. So the localization at the F is 0, but this exactly means that localization of the map phi at the F is surjective. So almost at the result 1. So we finished the proof of 1, now let's go to the part 2. Okay, so now we already have that, so we have 0, A localized at this element F, and then we have M localized at F, and then we have N localized at F. This is phi sub F. What we now know additionally that N is finitely presented, so then, and M is finite, so then clearly by the general properties of finite present modules, we can conclude that this AF is finite. Now it's the same trick that we've done already today. I localize in 2 steps. I introduce set T, so this is iota sub F, this is S, and then I can say that if I localize at the T module A localized at F, I'll get exactly localization of the module K. So again, I do localization at the set S in 2 steps. First I'll localize one element and then I'll localize the rest. But what I can say about the localization S inverse K? Well, here I assume that this localization S inverse phi is bijective. This means that this localization has to be just 0. And again, by the same logic as before, I have a finite module. Now this is a module over Rf, but still this module is finite, and the localization of this module is trivial. So again, I can say that there is an element. Now, to be more precise, I can say there is an element G. This has to be in localization of the ring with respect to the F, so it has to form some G prime divided by the F to the M, so which is the multiplicative set T intersecting the annihilator over the ring Rf of the module Kf. The same statement as before, but now this is just applied to the module KF, which is considered as a module over RF. Okay, and since this is in the D and also in the annihilator of the KF, I can claim immediately, take this module as the element G and 0. Help us to this conclusion. Okay, of course I can also say that I can take KF and localize this as the G prime over 0. Well, since in this module we'll bring KF, I already inverted F, and when I'm inverting G or inverting G prime, it's exactly the same thing. Because F to the n is already inverted on this module. So now I claim that I do the following. I just set H to be the product of the F and the G prime. And then if I localize K at the element H, then, if I want to invert F times the G prime, or if I consider fractions of something over F prime to the n, or at least I have fractions where I have some element K over F to the n, just by multiplying this by the element G prime to the n. So I can do this again in two steps. I can say that this I first localize with respect to the element F, and then I localize on the second step with respect to the element G prime over 1. So inverting H and inverting first F and G prime is exactly the same thing. But I already know that this is a zero module.
Localizing by H the same as localizing first by F and by...
But if you invert first F and then can invert this G prime, you definitely can invert H. Here you get fractions where your denominators like this, but you already have denominators F to the n and G prime. And whenever you are inverted H, you already actually inverted F and G prime, because you have a fraction like this, you just multiply this fraction, say by F, say by G prime to the n, then you get fractions of that leaves here, and then you can also. So now this element is exactly the element F in the statement. Now I can start with the element, and I see that localization of the kernel in this element is 0, and also localization of the element, localization of the module C and the H is also 0. Because when I invert again, I invert H, and I invert this F, and I already know this is true. Okay, first, from this proposition, so if one up to n that and generate the localization, now multiplicative set S, so then this multiplicative set such that same fractions generate localization just immediately follows from the first part of the proposition. So in this corollary, I just need to use statements because the proofs are more or less immediate. So you have this statement about the generators, you just apply this to a special situation where you have say that take module M, right? So you have module M, you have now submodule generated with elements. So now maybe you take as a map just embedding of this submodule into the module. Now you know that when you do this, the localization will be subjective, since element generated by the essence of this element generate the localization. So now
I is not from N to the submodule generated by M1 element.
Yeah, so take the submodule, embed this into the given module.
Where will be subjective map? Maybe inverse?
No, the inverse doesn't make sense. Okay, so the map is definitely here, so this is map pi. Now if you localize this map will be subjective. And so we need that this thing is subjective. So the localization is subjective, since this thing is generators.
Yeah.
So then we can claim that there's such element F. So essentially just this one map is the whole proof of this corollary. Now the next corollary is a little bit more interesting. So you take a module as before, and with this module you associate a subset that we call this UN. So this is the set of all prime elements in this R such that the localization MT and this prime element can be generated.
Proposition. In this proposition we have N finite, but there
So maybe we need to say that M is finite. So I just miss this condition. So let's say that the module M that we consider here is finite. So again, here M is finite. So it's a finite module, and we associate choose some number N, and we associate with this module and the number set inside this vector. So the claim is that this set is open. So of course it might be 0. So possible that, for example, take n to be equal to 1, and none of such operations is generated by one element, so it's just not enough generators, but at least we can claim that always this set is open. So this is asking people say that this is openness of the locus where modules generated by the n elements. And I think this is quite an interesting statement. And how we can prove this? Well, again, I'm thinking that it's enough to give you the statement because the proof is more or less obvious. Well, here you just want to say that whenever you have this condition, it is satisfied for some prime ideal, it is satisfied for open subset containing this prime ideal. Right? But now you just apply, for example, corollary the set S, which is just a complement to this prime ideal P, and this element F that exists. Right? So essentially, you just take as the open neighborhood. So this element F is in the localizing, the multiplicative set S, so in the R minus P. So this is not in the P. And hence, I can say that subset that I can use is just this. Like a corollary one, if this property is satisfied for P, this is satisfied for any prime ideal here, right? Any prime ideal that doesn't contain element F. Okay, so essentially this is something that we derived from the first part of the proposition. So now we're going to use the second part, where the module is finally, when n is finally presented and m is finite.
M is the subset of df, right?
And this is a subset of this term.
But is it a subset of df?
Yeah.
D of f.
No, dff is subset here.
Oh.
Now, I think I assume that localization at some multiplicative set is free. Free finite ring. So in other words, this is just isomorphic to the S inverse R to the n. So this is free module ring n. So then, there is element F in the module, sorry, in the multiplicative set S, such that at this module element F is free. More or less again, this follows immediately, just for example, with this exact sequence, while you can choose this thing to be a free module. Now the localization will be an isomorphism, and hence we can choose F such that the localization of the element here and here as well. And from this we can derive the last problem, and again that some locus associated with the module is open. Now in this case, again, I continue to assume that M is finally presented. So then the locus I will consider is UFM, and this is by definition in this type of R such that MP is free. So this is a locus where a module is free.
And where we use F?
F is not something that we use, F stands for free.
Oh.
So this is an open subset where module is free, at least stockwise. So then in this case, when module is finally presented, then this locus is again open. And the proof again follows from the corollary 3 and this observation that we can use principal open subset. This is openness of the locally free locus. Okay. The last topic in this section about local properties, we already know from the seminar that properties that like being free or being projected can be checked stockwise.
Say something like this open subsets, but n run of n. So
When we fix the rank,
yeah.
I think this is also true, and we did exactly the same.
Yeah.
One important observation, I don't know where to start, but maybe I start with this proposition. A couple of propositions. So I was saying that we can check stockwise for a module that module is, for example, projective. It's just what we do. The counterexample we saw in the seminar. I'm going to see maybe in some other seminars. But we can do actually this for flat modules. So the following are equivalent. So first property is flat. Yes, the property 2 and 3, all the localizations are flat. So MP flat, again, any prime ideal in this type of one. And any localization, any maximal ideal is flat. So clearly 1 implies 3. Is it clear that 1 implies 2? Explain this. Flat.
It's something like if you have sequence, but exact, and then we tensor it with M, it's still exact, and then we by P, it's still exact because localization is exact.
Yeah,
like
so
that.
something of that sort, but I would say maybe let's concentrate on 1 implies 2. So maybe we can say that this localization is also just then the product of these two things. We know this in general, but that is given to us that M is flat, and by general properties, any localization of a ring is a flat module. So this is then the product of two flat modules, and then the product of two flat modules is always flat. The product is So this essentially follows from the associativity of the tensor product. Take your exact sequence, you multiply this by this tensor product. Well, same as multiplying first with M and then with RP, but this preserves exactness and the product with RP also preserves exactness. Of course, this is not hard. Now 2 to 3 is trivial, 1 from 3 to 1. So let's take an injective map. You know that the tensor product with M is always exact on the right, but not necessarily on the left. So if you can show that you take injective map, take a tensor product with M and it's still injective, then this is exactly the same as saying that M is flat. So we want to show this is additional property meter. Well, this is what we want to show. Now I know that I can check injectiveness of any map of modules by localizing at maximal ideals. So this is injective if and only if stations are injective. This is already good enough information because we know something about exactly localizations and the maximal ideals. Now first notice, as you know, that such tensor product, localization of the tensor product is the tensor product of localizations. That again was some general property that we proved when we discussed localizations. Now, what we have? Well, if this is injective, then any localization, any maximal ideal is still injective. So since it is injective, this we know because localization preserves exactness, so in particular it preserves injectiveness. So this is injective, and then I take a tensor product over Rm with Mn, which is, I know, given to me property 3 that this is a flat motion. So injective and flat, let's say this is star is injective. Standard corollary is the following. Elements at 1 and n generally is the unit ideal, but only all localizations are flat. And we already know this combination of the proofs that we've done before. Exercise 5 the proofs that we need to combine to get this result. So let me say one remark. So it is true that 2m projective, but m is projective, m projective, 1m, and first we need to know that this apps generally the unit ideal. In check actually the modules projective, there is locally, but you cannot do this stopwise. So in this sense, these properties are current. Unfortunately, the proof of this statement for projective modules is quite complicated. So probably I just need a couple of lectures just to prove this one statement. So we're going to do this. So if you're interested in this, you can ask me and give you a clue. Because the original paper where this property was proved actually has a mistake, and this mistake was fixed later. And of course, it is clear, well, we know that any localization, so here I used this argument, I used localization to prime ideal, but of course we can localize at any multiplicative set with the same result. So the derivation is that any localization flat module is flat. Of course, any localization of projective module is projective. So can you show that any localization of projective is projective?
But isn't it false from exactness of localization? Like we know that P is projective if for any.
Well, I think these are complicated. One of the ways to show that module is projective is to say that there is a complement module such that this is isomorphic, so it's not free module. Maybe not use S because as you said, right? So that was one of the properties equivalent to being projective. Now you can localize this, and localization maps direct sums to direct sums and free modules to free modules. So with this logic, it is more or less immediately clear localization of any projective module is projective. So last time on the seminar there was a question about injective modules. Now, for injective modules, it's not even true that if you localize injective module, you can get an injective module. And of course, we cannot check injectiveness stopwise, so there is local.
Localization of a free module is a free module.
Yes. Well, again, think about what's a free module? That's a module of this form. So if you local, and you know that since tensor product is the direct sums, many direct sums. Again, direct sums of products and localization is a special case of tensor products. We know that this is a free module by definition of free module. So localization of projective modules are always projective. But this is a hard statement. Another remark might be the following. You can notice that any finite projective module is finitely presented. Take a finite projective module, and you'll get like this. This potentially some kernel. Since this is projective, this thing splits. So K is actually in this case a direct sum of the RPM. In particular, at least this is covered by 5. So this is again finite. So for projective module being finite and being finitely presented, it's the same thing. But now I'm playing that the following is also true, and this might be considered as an exercise. It's not as hard as this property. If M is flat and finally presented, M is projected. So it's not something that we can do in 1 minute, it's some thinking, but at least this is true. Maybe we do this on seminar, I'm not sure about the time, but you can, what's the theory is that flat modules and projective modules are actually quite close to one another. So for example, if you take an Artesian ring, then on Artesian ring being finally generated, finally presented is exactly the same thing. So on Artesian ring, finite module being flat and being projected is exactly the same thing. But of course this is not true. So this statement is not about finite module, this is about any projective module, not necessarily finite. For finite modules, say if you want to show that projectiveness can be shown very locally, for finite modules, say all the material rings, you probably can do this immediately, reducing everything to this. Okay, finally, the last statement about what projective and free modules. So now we know that everything can be, at least for flat modules, everything can be reduced to clockwise situation. So the question is, what we can say about flat modules over local rings. So we analyze localized prime ideal, then we need to analyze what are flat modules over such locals. And the last proposition is exactly about this. Let me call maybe this here, since this is an important statement. So Rm is a local Noetherian ring. But in this case, the following are equivalent. First property, that the module 3, so the following are equivalent for some module, for some finite module, or minus 3, f is projected, and for the canonical map to the tensor product of the maximal ideal. So over for finite module overall being pre-projected flat is the same thing.
How this canonical projection works? Just
No.
blind?
We're going to see this in the proof. What we already know. So 1 implies 2, since any free module is projected automatically. Now any projected module is always flat. So since projected module is direct summand of a free module and direct summand of any flat module is flat, this follows from the definition.
Yeah.
So 1 implies 2, 2 implies 3, and 3 implies 4. So let me say that this is clear. And 3 implies 4. I need to explain how I get this map. Well, this is just because you have short exact sequence. M is mapped to R and then do the quotient. So I take a tensor product of the short exact sequence with N. Let me send this quotient in the field K. This I have exactly on the right. Now this is the map. So if I know that the module is flat, it preserves exactness also on the left. So by the flatness I can add 0 and arrow here. This gives me the injectivity of this map. This is how 3 implies 1. Okay, we know that the module is finite. So we can take 1 to the n, take a subjective map to the module, and then it has some kernel K. I claim that the kernel K is also finite. Now this is because I assume that the ring is Noetherian. By any of this condition, so K is finite. Okay. Now let's take a tensor product with the maximal ideal. The short exact sequence. So of course I have canonical maps. M to the K. Sorry, this is not M. Sorry, this is just K. And this is the M. So I'm just saying that there is such canonical map for any module. So in particular, this is for this module, and this module. So these are 3 canonical maps. So if I have this canonical maps, and of course this exactness on the right. Now I want to apply the snake lemma. So the snake lemma, since I know that this map is given to me that this map is injected, so this is injected. So it means that there is no kernel here. So this means that if I consider co-kernels, I'll get short exact sequence of 3 co-kernels. So it will be, let me maybe give some names to these maps. So F, H, F, and G. So then by the snake lemma, I have 0 co-kernel of the H of the G. So what's the co-kernel of the map F in the middle? Now this is the quotient of the free module by just embedding of the maximal ideals and copies of maximal ideals in the free module. So this is isomorphic to the A to the N. Now co-kernel of G is precisely the quotient, precisely the tensor product of the same thing they can do. Anyway, so I can say this is tensor product of M and K, and this map.
Kernel of F. What is K?
K is here.
Yeah, okay.
And this is just n copies of this map. This map and this definition. There are some copies. So if you just look at this map, while in the Kayamas lemma, I can say that this map is surjective. Because I can take generators, or I can also say that this is the same as this function. I can choose generators of this vector space, leave this to the generators of the M, and hence I'll get essentially the elements that generate this free module the maximal ideal will be generators of this vector space. So this map is surjective. Now if this map is surjective, this map not just surjective, this map is actually an isomorphism, right? Because this is just vector spaces, and these vector spaces are generated by the same set of generators. So this is isomorphism, and hence co-kernel of the H is isomorphic to the zero.
Can you repeat, why is it isomorphism?
Well, this is an application of the Kayamas lemma. I take a module,
Yeah.
I take it as a product with K or this thing.
Yeah.
So that's a vector space.
Yeah.
In this vector space, I can choose a basis.
Okay.
So then I can leave this basis as generators of the module M.
Okay.
So do this by the Kayamas lemma. So consider submodule generated by these lifts, and apply the Kayamas lemma to show this is the same inside the module. So now we can think about here. This was any set of generators. So in this short exact sequence, I want to use this set of generators, the lifts of some bases in this vector space.
Yeah.
So then, if I consider again what I'm doing here, considering this generators module maximal ideal, so as vector spaces, these two things are exactly the same. Well, they have the same dimension. The map is surjective and they have the same dimension, so this has to be the zone.
Yep. Can you, okay, so we have bases in M tensor K. Yeah. Then we lift it. We
By the way,
set of generators, n generators.
Yeah. So they say this is n-dimensional vector space, and the same n will be put here, and the list of the bases here are generators of the module n.
Okay,
So this will be the k-dimensional vector space. This again n-dimensional vector space. This is n-dimensional vector space, and it's surjective. This has to be isomorphic. So anyway, so the co-kernel of H is 0. And what's the co-kernel? Again, while looking at this map, the co-kernel is precisely the k modulo k. So have a module such that you take this module the maximal ideal, you get essentially zero vector space. Again, by the Kayamas lemma, this implies that the module k is a zero module. That's exactly what we want. If k is isomorphic to 0, m is just a free module. Okay. So this is the end of today's lecture and the end of this section. So after midterm, we're going to start some primary decomposition.
Wait, when will midterm take place?
I don't know yet. So we need to choose time that satisfies, that works for all students in the class, so it might be quite hard. So in the worst case scenario, the midterm will be after the exam week or during the seminar. Любой коллективный модуль всегда плоский. Да, почему? Потому что это утверждает, что любое слагаемое тоже является плоским. Но это потому, что просто, например, примените, которую вы точно поставите с тремя членами. Соответственно, когда вы примените прямую сумму, когда замените прямой суммой, у вас будет сумма из двух правых, которые
складывается, что долго будет точно.
Да, соответственно, эта сумма будет точной, тогда это какая-то слагаемая точная.
Ну да.
Сумма плоских это